Hello, everyone. Today we have Erin Acquesta, who will be presenting, giving us a talk. She is a mathematician and principal member of the technical staff at the Applied Information Sciences Center at the Sandia National Laboratories. She received her master's and PhD from North Carolina State University in applied mathematics. Her research area of interest includes scientific machine learning, uncertainty quantification, sensitivity analysis, and machine learning explainability, with an emphasis on providing credible, adaptive, and interpretable modeling capabilities for enhanced situational awareness in support of national security decision-making. As a professional service, she is a member of the ASME VVUQ Standards Committee, writing definitions for verification, validation, uncertainty quantification, and credibility for machine learned models. She also volunteers her time for educational outreach as a mentor and head referee for the Albuquerque VEX VRC Robotics League and New Mexico State VEX VRC Robotics competitions. Okay, Erin, the floor is yours.
Great. Well, thank you, Rita, for the introduction. I'm going to go ahead and jump right in. So this is a wall of words. I always like to have this in my presentations. I'm not going to read it through to you. I just like my presentations a bit standalone and kind of set the stage and the scope of the discussion that we're going to dive into here in a second. But here, really, the emphasis is going to be more around the fact that we want to be able to support our decision makers with accredited and credible modeling capabilities during emergency response situations, like we saw during the pandemic response for COVID-19. This can also apply to a whole host of other areas like wildfires in LA recently, and a variety of other applications where we see complex systems modeling, where we know what's going on, but we don't quite have all the details, and data is kind of trickling in and providing more insights along the way. So we are seeing technology, the exascale computing and AI are providing greater potential for that effective decision-making at scale for high consequence, uncertain, complex systems. But we still have a challenge in managing all the many sources of uncertainties that are associated with the data, the models, and the computational methods. So I always like to start here to get into a little terminology, make sure we're on the same page. When I say trust, trustworthy, or credibility, I mean something very specifically. At Sandia, we put a lot of emphasis on the fact that trust versus trustworthiness has a distinction between the fact that trust defines the state of the decision maker, and really it's up to the decision maker whether or not they integrate our modeling capabilities into their decision-making process, and they may have more sources of information to baseline that decision off of. Trustworthiness defines the state of the model. So we hope that the model would be trustworthy, right, in the context of a variety of information, safety, security, reliability. We would do some red teaming, testing, and security analysis for these things. We want to know what bias exists and is accounted for, as well as you'll see a lot of varieties of trustworthiness will address. It'll either say robustness, model performance, reliability, right? We have a long history at the NNSA labs, and we would call this credibility. It defines the technical basis of the model. This is where we would establish the verification, validation, uncertainty quantification requirements, that the model is meeting our expectations, that the model is solving the right thing, and it's solving the equations correctly, and that we have the right equations usually, but it can mean a lot more than that. One of the things to highlight, I will address a little bit in AI. One of the things that can get a little dangerous is when you have trust, but you don't have the trustworthy evidence. We're seeing a lot of this, especially with generative AI, that these tools make society's life easier, and they want to use it, so they have trust in lieu of the evidence. What we're trying to always move towards is what this intersection here, what we would call the acceptance criteria. We have the right evidence that the decision maker can use to decide whether or not they would want to bring in this model into their decision-making process. But again, I want to emphasize that we have a deep understanding, not only at the NNSA labs, but really our federal regulators talk in the terms of credibility. But speaking from Sandia's perspective, what does that mean for us? We have this tool, it's called the Predictive Capability Maturity Model. It is based on Carnegie Mellon Software Engineering Institute's original maturity model that was designed for the DoD and now largely more managed by CMMI over at Carnegie Mellon still. We took those principles of a maturity model about 30 years ago and adapted elements that we would need to ascertain the believability of a model's prediction for high consequence applications. So this is a communication process that allows us to identify the elements that can go towards credibility evidence, but the key here is that we're always centered around an application context. So an example of an application context could be partial differential equations for computational fluid dynamics. So this is an evidence-based coordination of knowing what matters when we design PDEs for CFD models, and making sure we have the right physics, we have the code verification distinct from solution verification, proper validation, and uncertainty quantification. This is a process that you'll identify that there may be areas where you can advance the credibility, and so it's kind of iterative. You have to know how to right size and assess the appropriate analysis criteria. But I am going to touch base on some neural network modeling for model form error corrections. So one of the things that our teams are doing is we asked what happens when we change the application context to use machine learning or broader AI applications. So I'm going to kind of step you guys through some of these elements first to emphasize that data representation is essential. The credibility of any machine learned model is predicated on the data that was used to train it. We still care about the physics in the model, but we adapt the language of domain aware. This is what machine learning community uses to say, is the model aware of the domain phenomenology that we recognize or expect, whether it's physics, physical principles, biological principles, chemical, and a variety of other applications. We still want to be able to do something related to the code verification, solution verification. We are just careful now because we are no longer asking for solving the right equations. The whole reason you're using machine learned model is because you don't know the equations up front, right? You still want to know if you're solving the right thing. But we have to be careful because we don't necessarily have the right tools for our classic verification, but we do still need this code and solution evaluation criteria. This is probably one of our biggest gaps in developing methods, and actually one of the areas where uncertainty is starting to have more of a predominant presence than it has in the past. Solution verification, I've kind of combined that in our code and solution evaluations, and we're replacing that now with explainability, interpretability. Explainability is very useful, but from a rigorous mathematical, statistical, computer science perspective, evaluating that the fundamental principles are met for computational modeling, these explainability methods have a lot of room for development. They are largely a heuristic of a heuristic, and so we are investigating further kind of what elements of maturity would mean for different explainability and interpretability analysis. Uncertainty quantification validation, this is the area where we've done a lot of work already, right? And so there is work that's being done here. One of the things that we want to highlight and emphasize is that while the work is being done, when we talk about a maturity model, we don't really have the right tools to meet higher maturity. Let me tell you what I mean by that in the context of UQ, right? We're on the UQ seminar today. So these are the definitions, right? These are loosely the definitions we use at Sandia. The uncertainty quantification, we want to know how large the uncertainty is in the results. We can distinguish this between epistemic and aleatory, epistemic being the reducible uncertainties. We always want to be able to identify those so that if we could collect more data, we can gain more insights, we can gain a better understanding, we can drive down the prediction uncertainties. Aleatory uncertainty is just the fact that our world is inherently random. These are irreducible. Why does that matter in the context of a maturity model? So if we take just the element of uncertainty quantification, that's true in any aspect of computational modeling where we're considering whether it's a PDE or an AI ML model or a combination, a hybrid model, we actually are asking the question, how is that model going to be used first? Because then we know what kind of level of maturity we're going to be targeting for the model evaluations. So maturity is defined not only by how low to high consequence the decision is going to be made based on the model, but to what degree is that model the only source of information to make that decision on? So here's some examples that we'll see: scoping studies, design support, qualification or certification levels that we'll see in our nuclear deterrence application areas. These is language that we'll use in that context. But in UQ, level 0 would say it's mostly judgment only. You have a deterministic analysis. Level 1, you are propagating aleatory and epistemic uncertainty, but without any distinction. Level 2 says that these uncertainties are segregated and properly identified. And this is the biggest challenge we'll have with like the machine learned models. We've done a lot of work in PDE models or ODE models, some of our other computational modeling tools, but something like machine learning or our higher fidelity, more complex systems models, like I'll get into agent-based models here in a little bit, it's harder to segregate those uncertainties, and we don't really necessarily have the tools to do so. I'm going to keep kind of driving this point a little bit because I will be getting in a bit more into the AI and the ML space. So today, what we're seeing is NIST is setting the standard for AI trustworthiness. This is why that language mattered so greatly, and we wanted to make sure we have the same understanding and the term between trust, state of the decision maker, trustworthiness, the state of the model, and then credibility is the core technical basis. So these are the core building blocks that NIST set as requirements that we were working towards for AI trustworthiness, but they don't tell us how to do it. So what we've done is we've taken that credible technical basis that we've been working from with the maturity model and asked, okay, if I do proper assessment of data representation, domain aware, I have the code and solution evaluation done, explainability, right? Let's say I can do all of this for the right maturity level of the model. I'm going to map directly with the solid arrows here where I would expect to have representation of these building blocks towards AI trustworthiness. And then if I'm still doing that correctly, I would say indirectly, I would have some impact towards that safety, security, and resiliency. I asked a colleague of mine who works on that red teaming, testing, and evaluation side of things, when they look at things like the counter-adversarial, being robust against counter-adversarial machine learning attacks, cyber concerns, and evaluating its performance, where do they see that their tests are going to directly impact those building blocks? And theirs looks different. It is more wide-spanning, but they do still have direct. And then if they did everything correctly, they may have some indirect impacts on safety and then that accountability and transparency. But the key thing that I always like to emphasize is that with an anecdotal understanding of AI and lack of a more robust theoretical foundation, we are positioning ourselves at the precipice of knowledge when it comes to these AI tools. And I would argue that further work does have to be done to establish those theoretical foundations, because once we have them, we do have means to set regulations and monitoring and controls for safety when these machine learning and AI tools are used in the context for high consequence applications. So that I just want to kind of go over an overview, make sure we're on the same page with some of the basic terminology that we use quite extensively in this area, and kind of diving in, right? UQ is an element of credibility and is actually directly related to the verification verification validation questions, but it's just part of the bigger problem that we have towards trustworthiness. But even then, I'm going to get into a deeper dive now into the managing uncertainties and through a motivating exemplar where we use scientific machine learning for epidemiology. So in this context, I was talking about earlier how our modeling capabilities are starting to advance with Exascale and AI technologies that are allowing us to do more and learn more from data faster and be able to benchmark against some of our theoretical understandings of these complex systems as they evolve. This is a summary from the Government Accountability Office that outlines during the pandemic, this report came out. And I love this diagram. It's really important to share from a decision maker's perspective as we develop these computational tools, where the tools are most useful, when the information from models can be most useful is early response. But early response means I don't really know exactly what's happening. I have an idea of what's happening. We know how diseases spread in a host population, but this was a novel disease. I didn't have the right parameters. I didn't have enough data. I didn't have a full understanding as every day we got new data, new information about how to calibrate these models. This is where the models are going to be most useful. But it's not until the end of an outbreak when we have all that data that we can calibrate the highest fidelity models, right? These are when the models are going to be most accurate. So how do we balance this trade-off here? One of the things that we've been looking at Sandia is saying, start with your simpler models, something like a Bayesian inference model that can take the case count data and estimate an infection rate curve to get that push forward predictive curve to help decision makers look at how the trends are changing, how their policies are affecting that change, and when we're gonna, if we might be seeing a bend in the curve given the policy. Is this policy effective based on these quick analysis, directly data-driven Bayesian inference models? The reason why I'm emphasizing this in this context is that for epidemiology, for these systems that are inherently stochastic and evolving over time, we can't use stationary signals for our Bayesian calibration questions. We don't have a stationary likelihood. So in this context, like when I take a Bayesian inference model, it gives me a time varying uncertainty range that's informed by the data. One thing we'd like to do is see if we can use that estimation of the time varying likelihoods to now use a stochastic process for the likelihood in our Bayesian calibration of something like a system of ODEs. We have 100 years of experience. This is where we ground our epidemiological principles, are consistent with epidemiology modeling. These compartmental models are great because we can put them together quickly and we can be able to say a little bit more than the data-driven forecasting models can with the Bayesian inference. But they're still really underrepresentative of this highly complex system. So what we can do then, and what we'd like to do, is preserve that knowledge again that we're learning from the ODE systems, be consistent on a global scale about the disease dynamics on an aggregated mesoscale. You might want to interpret, right? But we want to be able to aggregate that understanding, preserve it, and then add the fidelity where the model form errors exist, integrating that into a network model and then even into an agent-based model, which is actually the target of one of our large DOE efforts right now. Okay, so I mentioned those compartmental models. They get a lot of scrutiny, they get a lot of pushback because there's a lot of simplifying assumptions about what they can represent during a novel outbreak. But what they do preserve is a lot of biological consistency with what we understand from an epidemiological perspective. So in this audience, it's really helpful. I don't think I have to dive into all the details of an ODE compartmental model. We've seen these before. We understand what they represent. The consistency comes in because lambda, this force of infection function, is going to capture a beta term. That's your rate of infection that your infected population is spreading to your susceptible population. There's where I'm starting with some biological consistency. Gamma, the rate in which my infectious population will be recovered in the dynamics. If I take the inverse of this, it represents the mean duration of infectiousness. So it's nice because I'm preserving a lot of those epidemiological consistencies. I'm interpretable, right? My parameters mean something in the application context. It also has, if I dive in deeper, I can dig in through bifurcation analysis and evaluate what the model R naught is. So if I get the model R naught, I can ask, this is our first line of defense. In epidemiology, we want to be able to remove the infectious population from spreading the disease. But we want to do that because we want to target down in the herd. We don't want to wait for herd immunity to spread out because there can be a lot of disease-related deaths in that context. So knowing what R naught is and how it matches what we're seeing, the data is telling us what R naught is, helps us further relate that model's accreditation for use for this for a particular virus spreading across a particular host population. And then that goes into the effective reproduction number that's going to take into account that the susceptible population is changing over time. And then we want to derive that herd immunity. So we can capture a lot and keep consistent with a lot of information if we preserve the core dynamics that we know, we trust, we love. We just know it wildly underrepresents the real world. So we want to be able to get some model form error corrections in there. So I'm going to take a moment again. Bear with me a little bit here. This is a toy example that I use to communicate the distinction between model form error and model discrepancy. So imagine we know a notional ground truth model. So I'm supposed to model this in the context of f of x and z of t. Often what happens is we know how to model X of t, which is what we have with the epidemiology models. We know that there's certain equations that are representative of the true underlying dynamics that we want to preserve. We just know it underrepresents the real world somehow. And sometimes we'll put in this z tilde. We know that that model form error matters. So we try to put something in that's an approximation, but it's just an approximation to what I should have modeled. This is your model form error. When you have a model form error, you're going to see in the solution space, no matter how hard you try to calibrate this green dashed solution to the model, to the data, you're always going to be left with this discrepancy. It's important to note that discrepancy is a comparison from the model solution to the trend in the data. You don't want to get anything that fits perfectly to the data because we all know the data has uncertainty inherent to it as well. So you look at the filtered trend of the data, you compare that to the model, and you find where you have model discrepancies. The reason why this gets emphasized, right, is because our model prediction uncertainty is a combination of model form error, parameter, estimations, data errors, and numerical error. We're really good at handling the parameter uncertainties, the data uncertainties. We're getting much better as a community in managing the model form uncertainties. Numerical error, we still assume to be marginal for the most part, but it should be emphasized, and it will be further emphasized, that with AI, neural network models in particular, when we integrate them into these dynamics as a correction term for that, what was missing, we have a lot of inconsistencies, and the numerical errors are starting to now have some influence in what we're able to learn in this context. So here's an example where we take a hybrid approach, partnering some folks over at MIT, and this is just a summary of what they did in the midst of the pandemic. It's a nice, simple example that we can still relay during our talks, where we've taken that SIR model I started with, and then said, okay, well, this is underrepresentative because it's not accounting for the fact that our contact tracers are removing the infected population from spreading the disease. So we add another compartment. We just don't know how to mechanistically design the rate of change because we know that it's much more complex because it's confined by resource constraints. It's, there's other aspects of where the folks in isolation may not want to stay in isolation. They're not necessarily going to be compliant to that. So we need a time varying rate. And what we do is we put in a neural network that's going to learn that model form error at the source by targeting a loss function that's going to look at the discrepancy in the solution space. So it's going to learn what is the model form error correction, given that I'm placing it in a particular, onto a particular compartment that I know is missing, but I'm trying to drive down the discrepancy over in the solution space. This is just an example of how we can see that impact throughout the world, really. Quite quickly, we can get a relative sense. There is still model form error to this, and we'll see it in the more complex example. But one of the things to note, you look at Spain here, and there's there's just an outlier week, I guess, that happened here, and it really threw off the model's ability to estimate this. So something to note, the reason that we can use these neural networks in our scientific machine learning applications is based on the universal approximation theorem. Universal approximation theorem says that if you have the right architecture, if you set the number of layers, you have sufficient neurons. If you set the number of neurons, you have sufficient layers and non-polynomial activation functions, that neural networks are a universal approximator to any continuous function. But in our case, we have no idea how complex or how simple the architecture needs to be for that model form error correction. So it's important to note that while the universal approximation theorem is a necessary condition for neural networks to be function approximators, in practice, it's not a sufficient condition. So we are going to have some numerical errors and some other model form uncertainty that's still rearing its ugly head in our context. So this section, I wanted to kind of motivate the discussion through the credibility analysis, largely because our uncertainties come from a lot of different sources. We started with an ODE model that we know is not credible. And so we brought in this neural network to learn our known unknowns. We know it's underrepresentative in a certain way. And so we wanted to add in that neural network to learn the model form error correction. I just talked about the verification challenges, right? That universal approximation theorem is a necessary but not a sufficient condition. There's a gap between theory and practice. These neural networks will also get stuck in local minima. And they're not always going to converge to the same solution every time. Largely, they're run by atom or some stochastic gradient descent. And so you're going to see some variability in the different approximations it can find. And then we'll take typically an average of those solutions. Validation challenges, we're asked, there's other validation challenges, right? Normally we would just take a calibration validation set. I still have a strict set of data that I can work with, and I now have to chop it up into more pieces. Now I have to train, test, and validate that data set. And we don't know what it means to have an established validation criteria for a known unknown, right? Uncertainty challenges, I wanted to drive down model form uncertainty, which is a result of that model form error that causes a discrepancy, but I brought in this black box to do it. And so I'm introducing, I still have the ODE parameter uncertainties, but I'm introducing the neural network parameters uncertainties, its architecture uncertainty, the numerical instabilities, and I still actually have model form uncertainty. When I showed you that example, I can match. Our MIT collaborators and partners did match the data, but it wasn't the right model form. And so to what degree does that matter? Should it still matter? How would we handle that? So getting into an example, the real world's hard. It's gnarly, it's difficult to know that you have learned the right thing in this context. So one of the things that we've done is we've said, well, hey, these UDEs can actually do something for us for calibration of these agent-based models. So we know that agent-based models are large, overly parameterized, high fidelity models that have ill-posed inverse problems, and a lot of different parameters that are operating on multiple different scales. And so we designed a workflow that we would be able to set up these UDEs as a surrogate to an agent-based model, which will then allow me to decompose my global parameters that I can preserve in those classic compartmental models that I know, I trust, I love, and they have identifiability. Those parameters map to the epidemiological principles. I know mathematically what they represent. I can get the proper bifurcation analysis to map and relate to the model R naught. On the flip side, though, I know every state, every municipality, every city has its own local nuances that I want to capture, and I can do that with the neural networks, but I'm going to do it first against an agent-based model. I'm going to assume my agent-based model is the highest fidelity version, and then because I know the design decisions of the agent-based model, I can then match and relate the UDE in that context. So what does that look like? Now I'm going to dive into, and this is the work most recently done by one of our teams here at Sandia. So I want to make sure I'm giving credit to Kyle Richker, Jackie Wentz, and Jody Bray for the work that they put into and leading this effort for establishing UDE surrogates for agent-based models. But more broadly, this is a very large DOE collaboration that's led by Lawrence Berkeley National Labs with Lawrence Livermore, Los Alamos, Argonne, Brookhaven, Sandia, in partnership with a couple of universities, Boston University and Morgan State. What we're doing is trying to develop the next generation of infectious disease modeling, taking agent-based models to Exascale in a way in which we have the proper vetting and criteria for that model in the context of its verification, validation, proper treatment of uncertainty quantification. Our team is particularly focused on the calibration question, which is where that the use of the UDs are going to come in. But for those that aren't familiar with agent-based models, these are your direct numerical simulation models, direct event simulation models. So we're not solving differential equations. We're just taking time steps using particle physics inspired applications for how the host can move and interact within a city. They're really nice because policymakers understand them better. When you go in with an agent-based model and you say, hey, I can model your entire population, where they're going to work, where they go to school. If you were to close down your local Targets or Walmart or other stores or businesses or schools, I can show you what's going to happen. That's very relatable to the policymakers, more so than our compartmental models are. Those are abstractions away from reality, and it's a lot to ask somebody to try to process what that would mean in this context. So they like these models. The problem is it's really hard to vet them for their predictive capabilities during a novel pandemic response. But it is nice because I can get an individual-based single community model that captures more of the complex mixing structures. So why do we want to use these UD surrogates? We want to be able to, so we want to design that compartmental model surrogate that allows us to be able to preserve what we know about disease spread, that 100 years of theory and application that we're familiar with. But we also need to be able to adapt that to the agent-based models that are stochastic in nature. They have controlled and uncontrolled sources of variability across every simulation. But these compartmental models, we're hoping are going to help us correct for that, keep some consistency about the dynamics while allowing the neural networks to make those corrections. So what Kyle and the team did first was say, okay, well, let's ask what happens when I use just an ODE model. So I have to start with some simulations from the agent-based model. The agent-based model is called Exascale Epidemiology Modeling. So what they did was they took a scenario from the Bay Area. They ran it for February 1st, 2020 to May 1st, 2020. So that first start of the pandemic. We had lockdown on March 16th. That'll always be illustrated with that dashed line in the middle. And what we did, they kept the same parameters, and all this variability is from the initialization. So 100 runs across 100 seeds for the ExaEpi simulations. So initialization alone can cause a lot of variability because it depends on where you put those first 10 infected cases to spread the disease and how many contacts they're going to come in contact with. That's true in the real world too, right? It depends on who's sick and who they're interacting with. But you're going to see this wide span of variability only from that initialization. So if we design an ODE model that matches the design decision of that agent-based model, they're both meant to capture the spread of the virus through a host population. And so they have the same parameterizations. We have actually designed this in such a way that we have independent parameters if we look at the dynamics of the system, not by the transmission rates, but by its fractional flows and the residence time of every compartment. From that, then we can actually calculate the transmission rates, but we're getting to independent parameters that are directly related to ExAPI. So we're providing at least a qualitative relationship between the model parameters. Further investigation has to happen that we have mathematical consistency, although we have been doing that work using subcompartmental ODE ODE models as well. Then we have some dependent parameters that we need for the design of an ODE model, but these are actually directly relatable as well to the latent incubation infectious periods that we can observe. Those can be derived out of those as well. The force of infection function is a bit more complicated. Our susceptible population can spread the disease, so can our asymptomatic population, but at a different rate. So we have a scaling factor for this. And we also know that 2 days before for COVID and a variety of different viruses, you can spread the disease, but again, at a slightly different rate. We assume that's the same as asymptomatic. Then in this force of infection, we don't have a beta. We have a probability of transmission because that's what Exaepi is going to do. Exaepi is going to say, I have these two agents, they got close enough, and there's a probability that my infectious agent transferred it to the susceptible agent. My beta is not the same anymore. So I want to pull out p-trans. And so now I'm going to add kappa. Kappa is the average number of daily contacts in the population, and that's going to be allowed to change over time because after I went into lockdown, I'm going to have an average number of daily contacts before lockdown, and then we're going to drop that drastically to account for the fact that everybody has been isolated or contained at home and isn't interacting with the same number of folks anymore. When I do this, this is the best fit of that OD model that we designed based on the design decision of the agent-based model. You can see in the susceptible context, we're kind of closer. There's definitely a discrepancy there, but our symptomatic population, those folks that are really spreading the virus, there's huge model discrepancy. So we know that there's a model form error in this model design. And so what we want to do is take our ODE approximation and bring in that neural network to be able to drive down that error term. And so we want to pull in the ODEs with the neural ODEs concept and have that hybrid approach where we preserve the dynamics we know, we trust, we love. We just need a neural network correction term. So what does that look like? We chose to target just kappa, right? We know that it's far more complicated than having a constant rates that then will just drop because we need to learn what the agent-based model, the complexity coming from the agent-based model is actually doing. And so we want to put in a neural network for our kappa of t. We're going to take this fully connected two-layer network that's going to spit out kappa at time t with some scaling factors that helps us regularize and manage the different scales that the neural network and the model is going to operate under. So this is a comparison. We still have that ODE model in there. We take our best ODE model fit with our best UDE model fits. We see that we have made progress and discrepancy in the susceptible population. We've made significant progress with that exposure population, blue being the UDE, red is still the ODE. We've made more progress in the symptomatic population, but this is an indicator that there's probably still model form error in our design of the UDE. What's actually pretty cool is we've been able to use these UDEs as a diagnostic to the ABM. For the first time ever, we're able to dig in and say, hey, you know what? This is the state that's not working. Let's go back to the code for the agent-based model and see how the design decisions were encoded. So that's been a really nice resource for us to engage with the model developers that are running these really large, complex particle physics-based models at Exascale on Perlmutter over at Berkeley. So we did also emphasize, right, a number of runs are going to cause multiple different solutions. And so this is that same plot of the 100 simulations of Exaepi in gray. In blue, in the dots, we have the mean solution of Exaepi that we're trying to match that UDE to. And so in the ensemble of runs, we can see that there is some variability in that approximation. But it's much tighter than the variability that exists across the entire agent-based model simulation. So when we learn kappa, we're going to have some outliers. We get a lot of variability in that kappa approximation. And so we're going to take a classic statistical approach to the loss, and we're going to cut out those that are 1.5 standard deviations away from the ensemble solution. And so we can actually see, which is kind of cool. Then we'll take an average, and we see this nice black average in the middle, that kappa model form error correction for the time varying average number of daily contacts in the total population. Before we had a straight, like we had a fixed kappa term before lockdown. We're actually seeing in the agent-based model that kappa kind of rises. There's kind of like the slow process of the population kind of interacting and growing and spreading the disease. So we see that ramp up as the disease spreads. There's going to be more average contacts. What average contacts means is something different than what we would think. It's an average number of daily contacts of the infectious population with the susceptible population. It should be growing a little bit as the disease grows, as the disease spreads, excuse me. And then we have that drop down. So I actually got to wrap this up. I would love to go into more details about then what we do is we look at functional principal component analysis because we want to get the mean pattern, and then we want to pull out the functional the basis functions from FPCA that are going to give us the main behaviors in a functional space of that kappa representation, so that when we do go to calibration, we're not calibrating that neural network. We want to calibrate parameters that provide that representation of that model form error correction. We've also tested and looked at next generation matrix methods to then look at R effective. So I said earlier, we want to keep that ODE model because it has so much biological consistency and mathematical properties about R naught and R effective. And so we can actually prove that for the UDE model, the effective reproduction rate, so this is the time varying version that is also based on the susceptible population, that we can actually derive that within the context of the parameters themselves. So we are actually getting to that theoretical guarantee of what the model is representing based on what we're seeing in the population. And what we see here, right, R naught, the CDC claimed was about, we're hearing like 2 to 4. This model is starting at about 4. And then the rest of the reproduction numbers are consistent with what we were seeing from CDC reporting. So that's a summary, but what I really actually want to do is I want to give a couple of last slides because this is the UQ seminar, and I want to really dig into managing the uncertainty in complex systems. And I have a few more quick slides that we can just kind of pop through and then go to questions here in a second. So this community, I'm sure, is very aware of Ralph Smith's book on uncertainty quantification that was published by SciML. This is a way for me, I take Ralph's diagram. UQ is not just the parameters. It is actually it's coming from many sources of the models, the experiments, and the numerical simulations. With models, all models are wrong, but some are useful. We know the model uncertainties that are inherent to our systems. Max Gunsberger is also quoted in this book as saying experimental results are believed by everybody except the person who ran the experiments, right? There's also limited data, incomplete data. There's even inaccuracies from sensors that should be accounted for in the data uncertainties. Numerical simulation computational models are believed by no one except the person who wrote the code. Right, and so now we have bug, bit flips, and other aspects of how the computational model could actually manifest other errors that can conflate our analysis and the uncertainties. This is something that shows what we diagrammed out for this agent-based model in this larger project around all the different ways that UQ in black throughout this diagram is going to pop up in our analysis. Even assuming the agent-based model is the highest fidelity model, you're still designing a surrogate. That surrogate is going to generate the synthetic data. That's going to require the full swath of parameter model form data, UQ, proper verification and validation. Our inverse problems from the real world data also has uncertainty inherent to it. And then the calibration steps are going to introduce additional uncertainties. This was just a first pass to help our team kind of organize and prioritize where we're going to tackle VV and the UQ elements of our analysis. We also brought in a neural network, and this is a diagram that another one of our colleagues here at Sandia put together a while ago of how many different ways uncertainty comes up in the design, the training, the data, the cleaning, the data, the cleaning, the design of the models, the different model choices for machine learned models. And there's a whole host of other areas that we would also want to prioritize as we start to bring in these neural network model form error corrections. But with that, I just like to close out when we're talking about uncertainty, managing uncertainty for complex systems models. We're starting to do hybrid models. Accounting for all the uncertainties is not necessarily what we have to do. We have to prioritize the ones we account for because, again, all models are wrong. Some are useful. I have this saying now that all data is wrong. It's in its aggregation, it's useful. Every data point you collect is going to have an error. There's no perfect precision in this world or our data collection procedures. It's in its aggregation that we have useful information that then has the uncertainties associated with it. And all subject matter experts can be wrong. We just hope we're mostly useful, right? So we have to be careful about the assumptions we put into the model form and its design. So this is just a way to try to organize, get people in a mindset that errors come in a lot of different ways in our predictive sciences, and organizing and documenting that helps us prioritize which ones we can measure, which ones we have data for representing, and where we should allow open not open, but sometimes just a characterization with a Gaussian process of the model form uncertainty is better than trying to add higher fidelity if you don't have the evidence to support that addition of the added parameterizations and challenges it introduces. So this is just my summary. I like the slide decks to be a nice contained representation of the information that was conveyed. So in the interest of time, I went a little bit longer, I think possibly, but I think we still have at least 10 minutes for questions if there are any. Thank you.
Anyone who has questions, please unmute yourself and ask Erin any questions you have. Well, I will start with one. In the Exascale model, I noticed that you are fitting ODEs and UDEs to the Exascale model average.
Mhm.
What is the motivation behind that? Because I'm thinking because just from the plots you show, the Exascale model seems to be highly uncertain in the outputs.
That's right. Yep.
Thus, targeting the average may not be something reasonable to do because you're basically asking for an individual model to fit to the mean.
Yeah, that's right. So it's a great question. And I did go back to the slide so everybody can see that, right? The gray is the 100 replicates of Exaepi just based on the initial seed and initialization. So the reason we are using the mean right now is because we have found that by doing so, this is allowing us to diagnose areas where the agent-based model had one intention for the design, and but then when it got encoded, we were able to find those areas where the encoding didn't reflect reality. So we had what we understood about the agent-based model. We can quickly take the average and then find where we're going to struggle to fit. And when we can find that quickly to struggle to fit, we can actually go back to the agent-based modelers and say, hey, we're seeing that there's still this model form uncertainty, and based on our discussions, we thought we had the same interpretation, but when we dug into the code, what actually got coded looks like it has, the inverse representation or something. This has actually come up where something accidentally got inverted in the code. And so we could go in there and say, I think this is actually representing the opposite of what you intended it to do. So it allows us to have a better communication tool with the experts on Exascale and building up these large complex particle physics-based models so that we can make sure that it's consistent with the phenomenology it's designed to represent. Now, with regards to the 100 runs, we do have an intern that has actually gone in and is fitting every single one of those, and then looking at FPCA to ask, is there consistency in the underlying function representation, even though we have large uncertainty across them? Would they just have a different parameter fit? But mostly we're seeing that the function representations are the same. So we're investigating that full variability space.
Okay.
Mhm.
So, just a follow-up. So you said you used ensemble modeling for the UDE. Can you talk more about that?
Yes. So the UDE has a neural network embedded in it, and it's doing two things. It is learning the model form error correction while providing the parameter estimation. Right? Because with a dynamical system like this, you know that every time we have an update to the model form error correction, you actually have a different dynamical system. And the parameters then of the baseline ODE model are going to have to shift because the model form has changed, because the parameters that match the data will be model form dependent. So it's training and it's learning both of those. But it's doing so using Atom. This is a stochastic gradient descent algorithm. And so every time you train it and you run it through and it meets the threshold and the criteria for the optimization problem we're targeting, which is driving down the discrepancy, we will get a slightly different answer. So we want to see what that variability looks like. And we can see it here. Can you see in the blue that there is variability across all those blue lines? That's 100 realizations of the training procedure for the UDE. We'd like to know that that is not all over the place, right? So we do run an ensemble to make sure that there isn't something else that we should be focusing on from the numerical perspective, that the training procedure isn't throwing in some major erroneous, a lot of different wild behavior. We have seen this with other examples when we're under-informed, which we will be when we go to calibration. Right now, we're doing a UDE surrogate, so we're taking all the states. The next investigation we've done on previous examples on other projects, we're asking, what data do we need to be able to learn a model form error correction and what parameters are going to be identifiable in that context? Because if you are underinformed on data representation of the states, you're not going to be able to learn all the parameters, all the dynamics, right? You may be underinformed, so we need to know what is the appropriate data that has to be leveraged to investigate. Otherwise, that training procedure will be all over the place. It's an indicator that you don't have enough information to use a UDE to get proper characterization of the dynamics.
Hmm, thank you.
Hmm.
I mean, I have more questions, but
Yeah.
let's see if anybody have questions. Just feel free to speak up. Otherwise, I will just ask my one more question. Okay, so I'll just indulge myself instead. So, wh- um, so still based on this, I can tell just from the nature of this problem, it's very difficult.
Hmm.
But even though we're here like trying to target the mean with ensembles, we can still see that from just from the plot, the coverage, or it's not really
Hmm.
good, even though we have
Mm-mm.
improved accuracy using from ODE
Yeah,
to
I like my hair.
UDE, the coverage from the ensemble modeling is not
Hmm.
great.
Mm-mm.
So
That's
what
right.
are your thoughts on this?
Yeah, that gets back to that diagnostic. This one right here, we have gone back to the team. The development is still underway, and we've been working with them to understand and dig into why we still have a major model form. There's still a major model form error that exists. So even though we've covered a lot of complexity and we've coordinated and we understand a lot of the dynamics that are in there, there's still a major area of underrepresentation that exists to be able to capture the peak. Or Or I mean, there's other ways to investigate this. It's back to the verification piece. Universal approximation theorems is a necessary condition for neural networks to be function approximators, but it's not a sufficient condition. So some of the other things that you'd want to investigate is, did I even have the right architecture to be able to learn the missing dynamics? So we can go back and investigate the architecture space now. A lot of this really is through investigation to understand how to make that fit. Because while we have the universal approximation theorem, we don't have much more theory to say how to design and train these algorithms, which is, you know, pretty similar to some of the challenges that we see in optimal control theory as well. Trying to find the right control profile, the optimal designing the right dual space to solve the optimal solution for controls, right? We're kind of in an analogous space here. It is very investigative, if you will.
All right, thank you, Erin, so much.
Mhm.
We're at the end of this seminar. Thank you again. Thanks everybody who came. So that's the end of our webinar.